The inspections of several tolerances will be explained in this video. All tolerance evaluations can be performed using only the actual data. However, for inspections of profile tolerances, both nominal and actual data are required. Firstly, flatness and parallelism are inspected on the beam feature. Then, diameter, cylindricity, and perpendicularity are evaluated on the largest cylinder. Subsequently, the angularity of the 45 degrees angle of the angular feature is inspected. Then, the position of the largest hole is evaluated. Next, the height of the largest step of the staircase is inspected. And finally, the surface profile of a hemisphere is evaluated. In this project, the actual data is already aligned to the nominal data. A tutorial for the alignment is given in the surface comparison video. For the flatness check, the beam plane needs to be constructed first. Therefore, we go to Construct, Plane, Fitting Plane. By pressing the Control button and clicking on the plane is automatically created. However, some areas of the plane were not selected automatically. Therefore, we click on the right mouse button and we choose for Select Deselect on Surface. In this way, we can select the unchosen parts of the surface. We name the plane Beam Plane 1 and we create and close it. Since the plane is created, we can perform the flatness check. We do this by going to the GDNT Quick Creation tab and selecting Flatness. By pressing the Control button and clicking on the plane, a flatness check is performed. In this menu, a tolerance value can be chosen. Right now, the flatness check is completed. For the parallelism check, both a datum and an inspection plane are required. First, we will create the inspection plane. As can be seen, some areas were not selected. Therefore, a manual selection is also required. We give the plane the name Beam Plane 2 and we create it. Then the datum plane is constructed. A manual selection is also required. And we give it the name datum plane B, since this name was also used in the research. We create it and close it. Right now, the datum plane has to be defined as a real datum. Therefore, we go to Construct, Local Coordinate System, Create Coordinate System. We will give it the name B, since it's coordinate system B, and we choose datum plane B. We create it and close it. Right now, we are ready to perform the parallelism check. We go to the GDNT Quick Creation tab and we select Parallelism. We press the Control button and we select the plane. We select coordinate system B as a datum system and we can define the tolerance value. Right now, the parallelism check is complete. For the diameter and cylindricity check, a cylinder is required. For the perpendicularity check, a datum plane is also required. First, we will create the cylinder. We press the Control button and the left mouse button, and the cylinder is automatically created. However, since not all surfaces were selected automatically, a manual selection is required. We name it cylinder 1 and we create and close it. Right now, the diameter can be inspected. We go to the GD&T Quick Creation tab and we select the dimension independency principle. When we select the cylinder, the nominal value can be defined, as well as an upper and lower limit. Right now, the maximum and minimum diameter are shown with blue arrows and as values in this box. Next, the cylindricity can be checked. We also have to define the tolerance value, and then we click OK. For the parallelism check, a datum plane is required. Therefore, we construct the plane first. We give it the name datum plane A, since this name was also used in the research, and we create and close it. However, we still have to define this as a datum plane. Therefore, we go to construct, local coordinate system, and create datum system. We give it the name A, and we select datum plane A as the datum plane. And then we press create and close. Finally, the perpendicularity check can be performed. We select the cylinder, we define datum system A, and we define the tolerance value. Right now, the diameter, cylindricity, and perpendicularity checks are completed. For the angularity check, both a plane and a datum plane are required. First, the inspection plane is created. A manual selection is once again required since not all surfaces were selected automatically. We give it the name Angular Feature Plane 1 and we create and close it. Then the datum plane needs to be constructed. Since the difference between the datum plane and the next angular plane is very small, this plane is created using a manual selection. We give it the name datum plane F, since this name was also used in the research. The coordinate system has to be defined. We give it the name F and we create and close it. Right now, the angularity check can be performed. We select the angular plane, we choose datum system F, and we define the tolerance value. Right now, the angularity check is completed. For the position check, both the cylinder, which represents the hole, and the datum system are required. First, the hole is constructed as a cylinder. A manual selection is necessary once more, since not all surfaces were selected automatically. We give it the name hole 1 and we create and close it. Then the three datum planes need to be constructed. We start with datum plane C. A manual selection is also necessary. And we give it the name datum plane C. Then we create datum plane D. And finally, datum plane E. Since all three datum planes are created, the datum system can be constructed. We give it the name C, D, E. We choose plane C as the first datum plane, plane D as the second, and plane E as the third. And we create and close it. Right now, the location inspection can be performed. We choose the hole. We choose datum system CDE. And we define the tolerance value. The location inspection is now completed. For the inspection of distances, two examples will be discussed. First, the distance between two planes with normals in the opposite direction is measured using the beam feature. On this feature, we will measure the distance between the left plane with a normal pointing to the left and the right plane with a normal pointing to the right. Then the distance between two planes with normals in the same direction is measured using the staircase feature. For this feature, we will measure the distance between this plane and this plane. Both planes have normals in the same direction, which point in the positive z direction. We will start with the distance between the left and the right plane of the beam feature. First, both planes need to be constructed. We will start with the left plane. And then we go to the right plane. Since both planes are created, we can now measure the distance between two planes. Therefore, we use the dimension independency principle. We select the left plane and we select the right plane. We define the nominal distance and we define the tolerances. Right now, the minimum and maximum distance is shown in values and also demonstrated using the two arrows. Now, the distance between two planes with normals in the same direction is measured on the staircase feature. The first step is to create both planes. We call this staircase plane 1, and then we do the same for the second plane. And we call it staircase plane 2. We create it and we close it. Then a surface point is created in the middle of each plane. Therefore, we go to Construct, Point, Surface Point. In order to create the point, the middle of the plane is selected, and we call it the staircase point 1. The normal is a positive direction of the z-axis. And we do the same for the second plane. We create it and we close it. In order to measure the distance between both planes, a projected point distance is used. This function projects the point of the lower plane onto the higher plane. Therefore, we go to Construct, Distance, and Projected Point Distance. Here we select the point of the lower surface, staircase point 2, and we project it onto the plane which lies above. We create it. So right now, the distance between both planes is constructed, and we can measure it. Therefore, we go to Inspection, check Dimensions, Distances, Distance. It will automatically select the created distance. We only have to define the nominal value, and we have to define the tolerances. So right now, the distance between this plane and this plane is measured. For surface profile checks, both nominal and actual data are required. Therefore, the nominal data is set to visible. First, the surface on the nominal data has to be constructed. Therefore, we go to Construct, Surface, Patch Compound from CAD. It's important to select all surfaces of the object, in this case the hemisphere, and we give it the name Hemisphere 1. In order to create the surface on the actual data, a so-called measuring principle is used. The measuring principle connects the surface on the actual data to the surface on the nominal data, and is constructed by clicking with the right mouse button on the surface of the nominal data, selecting measuring principle and fitting element. Since no manual selection is available, it is important to use fill gaps and fill holes to assure that all excess material is selected and thus the whole surface of the feature is included in the calculation. Right now, both surfaces are created. We can thus create the inspection, which is also located in the GDNT Quick Creation tab. We choose Surface Profile and we click on the hemisphere. We define the tolerance zone and we click OK. Right now, the surface profile check is completed.